Hello Precalculus student, this video is for chapter 4.7, Exponential and Log Models. In chapter 4.1, we have already went over some of the exponential models, exponential growth and exponential decay model when things grow rapidly in increasing rate, and we say the function that we can write is f of x or y equal to a0 e to the power k times x. Very often, if it is about times, and we would have kt instead of x. In a growth model, k is a positive number. For things that are decreasing rapidly but never reach zero, we can model the phenomena or the function values by exponential decay model. So this model decay that they decrease very rapidly and level off to a asymptotic towards zero. So the function that we can use is a0, which is the initial value, times e to the k x or kt, where k is less than zero. And actually k in both cases are the continuous growth rate or decay rate, represented in, of course, in decimal notations. When we're dealing with exponential growth and decay, very often we're dealing with very big numbers or very small numbers. So, and we usually represent them in scientific notation or describe them in order of magnitudes. And a logarithmic model can be used to look at numbers that grow slowly but take off. That takes off at first, but then steadily slow as time moved on. So it also can be used to describe order of magnitudes of very big or very small number. Logistic growth model is used to model situation where growth accelerates rapidly like an exponential model, but because of limited resources or other restriction in the growth, it would steadily slow to an upper limit. So the y value would not grow to infinity like an exponential model, but actually plateau to we call it a carrying capacity. So the equation is y equal to, or f of x equal to c over 1 plus a e to the negative bx. If when x is 0, the initial value is c over 1 plus a. When x approaches infinity, the whole a e to the negative bx would approach 0. So the end behavior or the carrying capacity is y equal to c, so the number in the top. The two additional model that I did not go over in this section, but the Newton's law of cooling is described in the textbook. So if you're interested in that, you can look at it. Basically, it talks about the increase or decrease of a temperature where the long-term behavior is not to 0 or infinity, but to the room temperature. When something cool down, it would gradually cool to the room temperature or the surrounding temperature. Gaussian model is used to model the bell curve, and we know bell curve has the equation of a e to the negative x squared over something. Okay, so that's used in probability and statistics. So the first things I want to do is logarithmic application, so log models. Like what I said before, it can be used to describe order of magnitudes, like magnitude of earthquake, pH values or water, pH values of water, and amplitude of sound in decibel. So we're dealing with very big numbers when we're talking about earthquakes. Say there is a particular way of describing the magnitude of an earthquake by the moment magnitude. So it is calculated by 2 over 3 log E, which is the energy of the earthquake, over E0, which is the smallest energy released by an earthquake. In this case, we define it to be 10 to the 4.4 joules, which is a measurement of energy. So in the 1906 San Francisco earthquake, we have the earthquake released 5 times 10 to the 16 joules of energy. So these are very big numbers representing scientific notation, order of magnitude of 16s. So how do we talk about it? So if you use this numbers to describe it, it's kind of difficult to describe how big it is. So usually we would use the moment magnitude to describe it. So what moment of magnitude would this earthquake be? So we could just plug it in. So m is equal to 2 over 3 log. When we have log with no base, that means log 10, right? E is the energy that is released in 1906, 5 times 10 to the 16 joules over E0, the smallest earthquakes being detected, like that. So this is just actually a plug-in. And you put in the calculator, and that would be equal to 8.2. Okay, so technically speaking, the magnitude of the earthquake in San Francisco about 100 years ago was 8.2. It's a really big earthquake. Okay, so and then there is an exponential. So with the second thing we want to talk about is exponential growth. And so over here, so we talk about the models for it is A0 e to the kt for continuous growth. Which is different from what we talk about, or actually very similar to what we talk about in chapter 4.1. We say a general exponential function is y equal to abx, right? So, or abt in terms of time. So in if we're talking about, so this talks about discrete growth. That means you grow at certain time period. So if t is a year, then you only can talk about it in like a year in the terms of years, whereas e to the kt is more general when you can talk about a continuous growth. A0 is equivalent to the a. Okay, so this is the continuous growth model, but there is also another model, which is we can represent something grow by, if we know the doubling time because it's grow rapidly, right? So if we know the time for it to double, say call it t, okay? The big T is the time to double. We can write the model by A0 2 to the power T over big T. So this is an alternative model other than ABX or A0 e to the KT, and so this is called the doubling time model. So how do I find the doubling time? We can solve doubling time by, if I have this model, how do I know the doubling time? We can say, oh, if it double, it will be 2 times of A0 is equal to A0 e to the kt, right? So how does the doubling time t associated with the cap of the continuous growth rate k? It turns out that this is the formula. But how do I A0, and we divide A0 on both sides because it's not 0. So 2 would equal to e of kt. I want to solve t so that it is double, right? So then I add ln because the unknown is t. ln2, ln e of kt. So by log properties, this can move to the front, and log ln e is 1. So that means kt, where t is the doubling time, is equal to ln2. So that's why t is equal to ln2 over k. So if you want to know how long it takes for something that grows continuously at a rate of k, you can use ln2 over k to do the doubling time. Or if we know the doubling time, we would use the we can use the a0 2 to the t over t to model it, and where t is the doubling time. Okay, so in this particular section in 4.7, we will look at the exponential growth model in more detail. So sometimes if we want to find the final number after a certain time, we can just plug in k and t and do it. If we know doubling time, then we can use a0 2 to the k over t. Now, sometimes they tell you a particular time and y value, but you have to solve for a0 and k. You would solve for a0, make a systems of equation, solve for a0, and then substitute to the other equation to solve for k. Um, Again, doubling times is t equal to ln k. K is also ln2 over doubling time. Okay, so these are the general approach to solve a exponential equation, exponential application. First question, first example. Initial population of a city is 23,000, increasing with a continuous growth rate. So recognize this term. Continuous growth rate means this is K. Convert it to decimal form. 1, 2, two decimal, 2 points before it will be 0.002. Okay, 0.002. Write the function that model the population t year from now. So that is a0. So we write it as you can use y equal or f of t equal. Both are fine. Equal to a0, which is 23000 e to the is a growth, right? 0.002 times t. So that would be the exponential that can tell you what is the population t years from now. Use it to find the population in 10 years. So that means substitute e equal to 10. So f of 10, that is the population at year 10 will be 23000 e to the 0.002 times 10. And then put in the calculator, I got 23,464.6. If you round it to whole number, 23,465. Okay. When will the population double in size? Well, we have K, so the doubling time would be equal to ln 2 over K. So that is ln 2 over 0.002. Put in the calculator is 346.57. If you don't have a graphing calculator or a scientific calculator, you can use decimal, right? So whatever that we did earlier, ln 2 over 0.002, that would be 346.57 years. So it takes that many years for the population to double in size because the growth rate is really slow. Oh, and then for the last one, that one you can do calculation as 23000. You just type G, I think, times e to the power of 0.002 and then times 10. So that's how you solve the 23465. Example 2. So these are pretty straightforward. I think A and B are repeat of what you have learned in 4.1. C is looking at doubling time by relating doubling time with K. The second question is a little reverse now. You were not given the initial value, you were not given the continuous growth rate, but you were given the population at two different time periods. After 10 minutes is 200. After 30 minutes is 1400. So this is time 1, y1, right? And this is time 2, y2. So if I use the exponential model a0 e to the kt, I want to find the initial size as well as k. So you plug in 200 equal to a0 e to the 10k, and then 1400 a0 e to the 30k. Now to solve it, first you rewrite this to write a0 in terms of k. So be my dividing e of 10k on both sides, right? Because we want to get rid of this to divide this one, e of 10k, divide e of 10k. So you have a0. So now, and then you plug this into the second one. So you would have a new equation a0 equal to 200 e of 10k times e of 30k. So now this equation doesn't have a0 anymore, it's just k. And then e of 30k divided by e of 10k, this is exponent division, so I can subtract 30k. So e of m over e of n is subtraction, right? E of m minus n. So 30k minus 10k would be 20k's. So it ends up being e of 20k. So now we only have one unknown in this equation, 200 e of 20k. K is the unknown. It is in the exponent, so we solve the exponential equation. Divided by 200 first, right? So this is totally divide 7 e of 20k. So then you would know that this is exactly what we have done before.